A curve is defined by the equation x squared y cubed plus 4x plus 2y equals 12. Now, notice that for this curve, y is not given explicitly in terms of x. In other words, we don't have y on one side and some function of x here. That's what's meant by giving y explicitly in terms of x. For example, y could equal 3x cubed minus 5x squared, whatever. So the right hand side would just involve x. So when that is the case, we say that y is given implicitly in terms of x. Now it may be possible to get y explicitly in terms of x. We could try and rearrange this to make y the subject. You can see that this first term here contains y and 2y contains y. We could try and put those terms together and bring everything else to the other side. Well, just bring the plus 4x over. Then we could try and factorize y out of this. And we could try and isolate y. But you see, that's not really possible. I factorized y out of this left hand side, but you can see that y is contained inside in this factor here. We can't actually get at y. We cannot make y the subject of this. So how are we going to find dy dx if we can't make y the subject? Well, what we do is we just differentiate this equation here term by term, each term with respect to x. So let's look at this term here and let's differentiate it with respect to x. But we keep in mind that when we differentiate y with respect to x, well, we just write down dy dx. So y is a function of x. So when it comes to differentiating y with respect to x, we write down dy dx. Of course, if we're just differentiating x with respect to x, well, we get 1. You know, the derivative of 1x with respect to x is just 1, the coefficient of x. Now notice here for this first term we have a product of functions, so we have to use the product rule. Well, first of all, I'll write down the statement of the derivative. So we're going to be differentiating x squared y cubed with respect to x. Then we're going to be differentiating 4x with respect to x. Then we're going to be differentiating 2y with respect to x. And finally, on the right hand side, we differentiate 12 with respect to x. So we differentiate the entire equation with respect to x. So we're performing the same operation on all terms of this equation. But for the first term, which is x squared y cubed, we have a product. So we have to use the product rule. So, you know, we have a product which can be denoted u times v. So when we go to differentiate the product, we take u, which is x squared, multiplied by dv dx. So we'd have to differentiate y cubed with respect to x. I'll do this on the next line, this derivative. Then we take v, which is y cubed, and multiply by the derivative of x squared with respect to x. Okay, so it's u dv dx plus v du dx. That's just a product rule formula used to get this derivative here. Now I might as well go ahead and actually work out this derivative. If we differentiate 4x with respect to x, we get 4. Just get the coefficient of x, which is 4. If we differentiate 2y with respect to x, what do we get? Well, that 2 is just a constant multiplied by y, so I can take that out. We get 2 times the derivative of y with respect to x, or 2 times dy dx. So when we're differentiating y with respect to x, we just write down dy dx. And dy dx is what we're looking for. Now what about the derivative of 12 with respect to x? Well, 12 is just a constant, it's just a number. The derivative of a number with respect to anything is 0. Now, we have x squared times the derivative of y cubed with respect to x. Now here we can use the chain rule. It's like we're differentiating something in brackets cubed. Y, you can think of y as like being something, an expression in brackets that's cubed. So we take the power that the expression is raised to, which is 3, multiply in front of the expression, which is y, take 1 from the power to get 2, so we get 3y squared. And then we multiply by the derivative of the expression in the brackets. So you can think of y as being some expression in brackets. So we're just applying the chain rule here. So we differentiate y with respect to x. So we get 3y squared dy dx when we differentiate y cubed with respect to x. That's just the chain rule. What about here? We have y cubed times the derivative of x squared with respect to x. Well, if we differentiate x squared with respect to x, we get 2x. Now the next step is to solve for dy dx, is to isolate dy dx. Gather up terms at dy dx on the left hand side, bring over terms that don't contain dy dx to the right hand side. So here I factorized dy dx out of 3x squared y squared and out of the plus 2. And I've brought over y cubed 2x plus 4 to the right hand side. And finally then we just divide across by this expression here, and now we have dy dx. Notice that dy dx is given in terms of both x and y here, not just in terms of x. You can check your answer here by typing the word differentiate followed by the function, and here's the result. Y prime of x is another way of writing dy dx. The 2 has been factorized out of the numerator. In part 2, we want to show that the tangent to the curve at the point 0, 6 is also the tangent to the curve at the point 3, 0. Well, if you want to see what the curve looks like, you can type your function in here and hit return, and you can get a graph. Of course, you don't need to have the graph to answer this question, but I'm going to use the graph to explain what this question is all about. So, we're interested in the tangent to the curve at the point 0, 6. Well, there's the point 0, 6. As you can see, it's a point on the curve. So if you plug 0 in for x and 6 in for y, work out all of this expression, you should get 12. So 0, 6 has to be a point on the curve, of course. So we're interested in the tangent to the curve at this point. And we're also interested in the tangent to the curve at the point 3, 0. 3, 0 is actually this point here. It's a point on the x-axis. So you can imagine drawing a tangent to the curve at the point 3, 0. And that tangent should also contain the point 0, 6. Well, that tangent should also be a tangent to the curve at the point 0, 6. 0, 6 is not actually the maximum value. The maximum value is a little bit to the left of the point 0, 6. This is what we have to try to show. That the tangent at 3, 0 is the same tangent at the point 0, 6. Well, we can start by getting the slope of the tangent to this curve at the point 3, 0. We can write it like this, dy dx at 3, 0. So we plug 3 in for x and 0 in for y. Dy dx is the slope of a tangent to the curve. And at 3, 0, well, this will just work out to be minus 4 over 2, which is minus 2. So we see we get a line with a negative slope, and that makes sense here actually. As a matter of fact, if we look at this diagram here, this distance here is 6, and this distance across here is 3. So we rise over run. 6 divided by 3 is indeed 2. And because the line is going in this direction, the slope is negative. Now, if we get the slope of the tangent at 0, 6, that means we want dy dx at 0, 6, you will see that we also get minus 2, because there are zeros in here, so this is 0 and this is 0. So we minus 4 over 2 is minus 2. So what does that tell us? Well, that tells us that at the very least, the two tangents are parallel to each other. So the tangent at the point 3, 0 is parallel to the tangent at 0, 6, because both tangents have the same slopes. It doesn't tell us that the two tangents are equal to each other, but it does tell us that the two tangents are at the very least parallel to each other. So you could easily imagine a tangent at 3, 0 and another tangent at 0, 6, a different tangent that's parallel to this tangent here. So how do we prove that the two tangents are the same? They have the same slope. remember now we won't have a graph to help us. So what we could do is get the equation of one of these tangents. So what I will do is I will get the equation of the tangent that's passing through the point 3, 0. We have the point and we have the slope. We have enough information to get its equation. So we have y minus y1, which is 0, equals m, the slope, which is minus 2, times x minus x1, which is 3. So what does this simplify to? This simplifies to y equals minus 2x plus 6. So that's the equation of the tangent passing through the point 3, 0. Then what we do is we take the point 0,6 and see if the point 0,6 satisfies this equation. And if 0,6 satisfies this equation, then that means that 0,6 is on the tangent passing through the point 3, 0. So we write this out, replacing y with 6 and x with 0. 6 equals minus 2 times 0 plus 6. Is this true? It is. We get 6 equals 6. So that tells us that 0, 6 is on this line up here. Of course, we could have done this the other way around. We could have got the equation of the line through the point 0, 6 and then show that the point 3, 0 is on that same line. So now we know that this tangent here is passing through, well, this line here is tangent to 2 points on the curve. It's a tangent at the point 3, 0 and it's a tangent at the point 0, 6. Its slope is minus 2. A point to notice from this graph is that 0, 6 cannot be a local maximum, because if 0, 6 was a local maximum, then the tangent at 0, 6 would be a horizontal line. It would look like this if 0, 6 was a local maximum. So that can't be the case. So 0, 6 must be a point that's near the local maximum. So if I just maybe draw out this part here, 0, 6 must be a point like that. Must be close to the local maximum. So we have a tangent at this point 0, 6 with a slope of minus 2. And it also happens to pass through the point 0, 3, or sorry, 3, 0. It happens to be tangential to the curve at 3, 0. So the slope of the curve at 0, 6 and at 3, 0 is minus 2. It's the same. Slope of the curve at both of these points is the same.